We continue with Stokes Theorem. So in this example, I'm taking my surface to be the cylinder. Remember, the cylinder equation is x squared plus y squared equals something, but I'm restricting myself to the z values between 0 and 1, and I'm taking a function f as y plus 2z, x squared plus z, and y cubed. Again, we want to look at Stokes Theorem. So remember, for Stokes Theorem, we have two parts. We have the surface itself. So in this example, this is my surface. This is where you start at 0. This is you stop at 1. This is your surface. So in this example, the top and the bottom, they are not included. And what is the meaning of this equality, by the way? Z is bigger than or equal to 0. That means this is included, but not the disk. So this is an open disk. This is an open like that. So the top and the bottom, they're not included in my surface in this example. So in this example, we have two opening curves. This is one curve. So the surface is open from two directions, from the top, from the bottom. So let me call this surface C1, this surface C2. So in this example, the opening curve is consisted, it consists of two curves, C1 and C2. Now, the orientations of these curves, they are extremely important. So for example, for the top curve, do you take this orientation or the other orientation? Do you take this for the bottom or the other orientation? We'll see all these details. But for now, so we are computing, so in Stokes Theorem, we have the line integral over the curve. We have to do it in two steps. So for C1, we need to have a parameterization. This is a circle, so the best parameterization is this. The z is 1 in this case. Of course, the t is between 0 and 2 pi. Now, if I take my parameterization like this, cosine t sine t1, this is exactly this red orientation. So I am taking the orientation this way. Why is it this way? Because remember, if you're talking about the x, y, z axis, this way, this parameterization gives you this orientation in the xy plane. Okay, but again, I'm not going to talk more about the orientation. We'll see it later, but let's do the computations. So in doing the curve integral, we need the derivative. So the curve integral over C1 is going to be the integral from 0 to 2 pi. Substitute the parameterization into the function dot the derivative of the parameterization. So the first component of the function was y plus 2z. Y is sine t plus 2z. Z is 1. X squared plus z and y cubed. So this is from 0 to 2 pi minus sine squared t plus 2 sine t plus cosine cube plus cosine t. Now the nice thing is this is 0, this is 0. If you integrate it from 0 to 2 pi, they will be 0. But by the way, this is minus, this is minus 2 sine t, and also the sine gives you 0. So now what's left? We're just having the integral from 0 to 2 pi for minus sine squared t, and this can be done easily using the half angle formula. Again, cosine 2t will give you 0. and this is the minus, and what's the answer? This is just minus pi, okay? This is just minus pi. So we computed the integral. So what is this answer? This is C1. C1 is this curve, the upper curve of the cylinder. It is minus pi. Now we compute the integral over C2. So for C2, again, we still have the same parameterization. The only difference is between C1 and C2 is that instead of having 1 here, it will be 0. Because C2 you are laying down on the xy plane. So the z will be 0. That means the 2 here will be 0. The 1 here will be 0. That's it. All other computations will be exactly the same. So basically, if you compute the other integral, so if you compute it, double check these computations, in fact, you will get the same answer exactly. And please, this is just a coincidence. If you have an upper circle, a lower circle, it doesn't mean you will have the same value of the curve integral over these circles. But in this example, we explained why. Because the only difference is in this one, in this two, in this one, but these numbers did not change anything in the integral. The terms corresponding to this stuff gave 0. That's it. Okay. So now we say, okay, so what's the integral over the curve? What is the opening curve in the Stokes theorem? It's the opening. If you look at the cylinder in this example, you have 2 openings. So you need to look at the upper curve, the lower curve, then you add them. But the question is, do we add minus pi plus minus pi, or pi plus pi? Or maybe pi plus negative pi, or negative pi plus pi. So what do we do? In this example, what should we do exactly? Do we take negative 2 pi as my final answer, 2 pi, or 0? This will be my question. So for now, I'm not going to spend more time on the orientation. You will see the answer by yourself after we compute, and then I will explain to you exactly how to select the orientation. So now let's go to the surface integral of the curve. Of course, we need to find the curl. Remember, the curl is nabla cross f, which is the I jk d by dx d by dy by z. The f components are y plus 2z, x squared plus z, y cubed. You compute what's with the I, it's a 3y squared minus 1. What's with j? The j has a built-in negative sign, so you remember it has a negative sign. Then it's 0 minus 2, so it will be positive 2. And with the k, it's 2x minus 1. So this is the curl. Okay, after doing the curl, you need to find the parameterization of the surface. Again, this is your surface. The surface equation is x squared plus y squared equals 1, and the z is between 0 and 1. So basically, you are taking r, let's say of r and theta. Now the x and y are related. The x and y are related via this formula, cosine theta, sine theta, and the z is free, so I'm calling it just r. Okay? The theta, of course, is between 0 and 2 pi. The r is between 0 and 1. These are the z values. Now you compute r sub r cross r sub theta. That's the normal vector, remember? So I, j, k. R sub r is 0, 0, 1. R sub theta is minus sine theta, cosine theta, 0. So when you compute this, what is with I? With I, it's minus cosine theta. With j, it's minus sine theta. And with k, it is just 0. Okay, so this is your normal vector. Now you compute. So now what is, at this stage we say, okay, what is the surface integral of the curl? It is double integral. What? You go to the curl, this is the curl. This is the curl, dot the normal vector, of course dr d theta. Now the normal vector is minus cosine theta minus sine theta 0. And what is the curl? The curl is a 3y square, the y is sine, so 3 sine square theta minus 1, 2, and 2x minus 1. Okay? The theta is from 0 to 2 pi, the r is from 0 to 1. Now we compute this integral. So this is from 0 to 2 pi, from 0 to 1. What is it? It's minus 3 sine square theta cosine theta plus cosine theta minus 2 sine theta, all of this, dr d theta. Now you can easily see, you can just right away, this is 0. What's this problem? This is 0, this is 0, this is 0. So in the end, my final answer is 0. Okay? My final answer is 0. Okay, so please, what is the summary? We had this cylinder. Now it's very important, okay? We have this cylinder. We have two opening curves. This is one curve. This is the other curve. We computed the curve integral on both curves. We computed the integral over this curve and the integral over the other curve. We chose this orientation. The answer was, just to make sure, negative pi. The same for this. We computed this orientation. The answer was negative pi. I'm taking a different color. So if you select the other orientation, you will get pi. If you select the other orientation, you will get pi. Now the nice thing, when we computed over the surface itself, the answer was 0. Okay? So now we know, going back to these numbers here, we know that this is not my choice. This is not my this or this are my choices. So how do we tell if this or that choice must be considered? The idea now is the orientation. This is exactly the idea. So what is the orientation in Stokes theorem? Let me go back to the beginning of Stokes theorem when we discussed this orientation idea. We mentioned something about if you imagine yourself, this is you, if you remember, if you imagine yourself as the normal vector looking at the curve, then the curve must be oriented counterclockwise, okay? Counterclockwise. This is the main idea. So going back here. Imagine you have this normal vector for the surface. So this is you, okay? This is you. Imagine you are standing like this. This is your head, okay? And you are looking to the top, you are looking to the bottom. You are looking to the top curve, you are looking to the bottom curve. Now the question is, if you look up and you imagine this as a watch, you imagine this curve as a watch, what is the counterclockwise? How does this watch go? Can you imagine it? The red orientation is exactly the clockwise orientation. The blue orientation is the counter. This is the counter clockwise orientation. If you look down to this curve now, in this case, the red curve is the counterclockwise orientation, the blue curve. So imagine if you look here, if this is your watch, just look at this. And you are looking from the top, this is you, okay? This is you. You are looking down here. The blue orientation is the clockwise orientation, but the red is the counterclockwise orientation. So in this case, this is the counterclockwise. Okay? But how did we tell if we look, if we take this and is it the outward? Is what we computed here for our cylinder. This is our normal curve for the cylinder. Is it the outward or the inward? Of course, in this example, it will not change anything, but we need to know it. Is it? It's not, in fact. If we take again a new figure, these are the axes. This is very important to understand. So the x is negative cosine, the y is negative sine. So if you take any point, the x is negative, the y is negative. If you take this point, the normal vector will be pointing downward like this, or in fact, like inward, like this. So the normal vector that we computed, is the inward normal vector, okay? The normal vector that we did here is the outward normal vector, but the outward normal vector gives you negative the inward normal vector. So this answer is still 0, it's negative 0. Now, the crucial thing, how do we take the orientation for the curves? So one of the curve was pi, one was negative pi. How did we tell that? We must change the orientation here. So remember, we computed this integral, but then we decided to change these signs. We decided to go with positive pi for the upper curve and with negative pi with the lower curve. The reason is, if you stand here and you look at this watch or this watch, we need to take the counterclockwise orientation. So this has to be pi, this has to be negative pi, and now we say, okay, we go back, and we say for my curve here, I am taking, this is a bug in the apple, by the way. We must take pi plus negative pi, that is 0. I hope this example makes the orientation in Stokes theorem very clear.